That's what you missed so far.
This is master set 26. I have a question for, problem 4 and problem 5. They're the same problem, aren't they? Like just about, I don't have a copy of it. Does anybody have a copy of it?
It's just the graph that changes.
Yeah, I think it's just the graph that changes, right? But part A and part C is gonna be the same.
A is definitely the same, and C is the same because we're outside the sphere, therefore we treat
I
it as a
thought so
point
too.
charge.
Yeah, so the only thing that would really change would be
Of
the graph.
right, the potential once you get to inside the sphere. Outside the sphere, it's the same, but inside, yeah.
Can you show how to graph that? Also, for the graph, what would be our zero? So.
Wait,
for-
where
would our zero be?
the potential zero?
Mm-hmm.
I thought I set that for that one to be an infinite distance away.
I think, yeah, you might have.
Yeah, let the potential be zero an infinite distance away. It's when I'm setting up the problem, uniform charge dielectric, solid sphere of radius A equals 8 centimeters, carries a total charge of 2 equals 5 microcoulombs. And then I say let potential be equal to 0 an infinite distance away. In other words, setting the constant equal to 0, back to what I started with. So if this is 8 centimeters here, so outside, we just, if I'm plotting potential versus distance here, it's, since the charge is uniformly distributed, I can treat it like a point charge. Spherically uniformly treated, I can treat it like a point charge, and so we're just dealing with the point charge formula in terms of the graph.
So all we're doing is finding the points and plotting.
No, well, you have to do the whole thing inside. So then, once you get to here, once you get inside the sphere, now we take a look at two things. One, if conductor, which I think is the second one.
Yeah, the second one's conductor.
So if it's conductor, what is the electric field inside a conductor?
Zero.
Yeah. Remember that this is equal to the negative gradient of the potential. In other words, the negative slope of potential, which tells me that the slope of the potential is 0 for the conductor.
Okay, yeah, that's what I had for the conductor. The one that kind of confused me is the dielectric
Okay.
sphere.
That one, I think we had done something in class where it was like that one was like that, the dielectric, was it going up from the origin to meet the graph?
The electric field is.
Okay. Yeah. The electric field, okay.
Zach? Or Zachary?
When you're isolating whether or not it's a conductor or an insulator, for some materials they're very similar. What constants or material values in the tables are you looking for?
Sorry, this,
Determining conductance versus an insulator.
oh, whether something is an insulator or a conductor?
What values and to what degree would you look for?
I'm dealing with a nice ideal world, it's a conductor or it's an insulator. I don't quite sure at what point it's officially one or the other, actually. I know that if you look at things that are labeled as conductors, they're usually 2 orders of magnitude greater in terms of resistivity, which we're coming up to later on today. Or conductivity, which is the reciprocal of it. I think that's generally what you look for to determine if it's considered an insulator or a conductor. Nothing is pure one or the other in reality.
Right, I was looking through the Encyclopedia of Physics and Chemistry, and I saw the tables for like permittivity and conductance and resistance. I was just wondering if you had some like staple values for
No, I
identifying
don't.
betwixt materials.
No, that from a physics point of view, that would be the solid state physicists. I just didn't had some solid state physics, but, yeah, I don't know, any cutoffs that they have.
Okay.
All right, so if we look at the dielectric or insulator, I know that my electric field, it's a 1/r squared value until I get to inside, and then it's linear. And I believe last time we derived the fact that that linear relationship right there. So my slope of my potential, my slope of my electric field is positive, and so, or take that back, my electric field is positive, therefore the slope of my potential is negative, because I got this negative sign right here.
So then it would go like that.
So it's gotta be going up somehow like that. I know that when I'm close to the origin here, that my electric field is 0 or small, so my slope is small. So it has to start out with a slope somewhere around 0. It has to be negative pretty much the entire time. So it's gonna be something like that. Sorry, I lost it, I didn't compose. Alright, is that, I assume that answered your question, or?
I did.
Just to confirm, test is still in March, correct? Test is still like a week away, or today?
Yeah, 2 days
Okay.
away. We should probably talk though. Yeah, the fancy sophistication of pen and paper. Alright, other questions? Marisol, you look like you have one.
Yeah, I have another one.
Okay.
For problem 6, it's also master problem 6. So, 6A, we derived an equation, but that's because it was symmetrical because the point was right in the middle. It was
Right.
4, 4, but when the point changes on part B to 2, 3, that's not really symmetrical with the,
Right.
so.
So, in that particular case, because I think sorry, I jumped ahead of, I knew what your question was gonna be, sorry, did I cut you off too soon?
No.
Alright, so we started out without a liner charge here, and what is the electric field at that point?
Mhm.
Then the next question is, I've got a line of charge, and what's the electric field at that point where it's symmetrical?
Yeah, that was the first one, and I knew how to do that one, but the second
was the
one, wherever
second.
the,
So one approach to doing this one, and I know you said you got this one, but one approach to doing this one is I can treat this as, well, like basically that problem right there, and then double it. Because I know through symmetry that the vertical components are gonna go away, it's the horizontal component that's gonna survive. So I could just solve for the I hat part, double it, and that would give me that. Now, when I move this point from smack dab in the middle to 2, 3, I could treat it like that problem right there, and then that problem right there, and add. Or, you could go through and mess with the limits of integration. Also from the previous, there are 3 problems that you could go through the calculus for this one right here, and then just apply that to the other 2 problems, or you could basically go from scratch and use calculus for all 3 of them.
okay.
Is that sufficient?
Mhm.
I do want to point out, and this was a common mistake, that's pretty much a common mistake every semester. When this was going from 0 to 8,
0 to 8.
4 is me.
0 to 8, sorry, when, that problem right there, oh, this was 0 to, say, y, something like that.
That's the first problem, so
Yeah.
0 to y max.
All right, so y sub n. And this distance here is y, that distance here was x sub 0 or something like that.
Yes, sir.
And so r is the square root of y squared plus x sub 0 squared. When you now, if you're doing this from, that's 0 to 8 there, that's a y, not a 4. Recognize that that distance right there is not y. That distance right there is y minus 4.
Yes.
So if I'm doing my limits of integration,
0 to 4 and then 4 to 8.
or r here is going to be the square root of y minus 4 squared minus x of naught squared. And if I'm doing it this way, y does go from 0 to 8. But if I just treat this as y, basically what I've done is I've taken my x-axis here and I've shifted it up. So if I just want to do y squared, then basically I'm integrating from -4 to 4.
Multiple by 2 for the 0 to 4.
So it's like a U sub. It's like a U substitution.
Yeah, yeah, it is. And so the most common mistake is to do y here, just like you did up here, and then still integrate from 0 to 8, and that,
When you're
Multiple by 2 for the 0 to 4.
when you're looking for the electric potential instead of the electric field, will it be the same way, kind of?
it's the same approach, except you don't have to worry about components, which is a nice bonus.
Giancoli shows the method of maintaining cosine rather than solving for theta. You
Wait,
solve.
sorry, say that again?
Giancoli shows the cosine method rather than replacing with the square when you multiply it out. So instead of solving for y, you solve for theta.
Oh, okay.
Or, no.
So
instead of
they,
solving-
so they put the integral in terms of theta as the variable?
Yes,
Ah, okay.
for some of them it simplifies it, for others it doesn't.
It's like finding the volume of a sphere. You can do it in x, y, z coordinates, or you can do it in spherical coordinates. One's a lot easier than the other. All right, and now for the world to be able to cherish for years to come. I tie my shoe. You're welcome, YouTube. Other questions?
Yeah, I have
Oh,
one
okay.
from, let's see, this was the spring 2016 test.
Spring 2016, okay.
There are no solutions for those, right? Online?
That's
I'm not
possible.
Sure, probably. I didn't look at them.
To come up with the typed out solutions for those takes about 3 or 4 hours, so it just, I think at this point, posting tests has outstripped my posting solutions, but.
Yeah. But it's, an electron is shot into a 9 meter by 14 meter room traveling 20 kilometers per second, I hat, at point A, initially heading for point B. So it's graph. As soon as it enters the room, it enters a region of a uniform electric field in the positive j hat direction, and it ends up hitting at point C. What is the acceleration of the electron for part A, and part B is what is the electric field strength?
Yeah, okay. Yeah, that, I assume that's the one without the story?
Yeah.
Yeah, I really like the story on that one. The students were less enamored. Wasn't as convoluted as the Valentine's Day 251 story.
Yeah.
Oh, yeah.
And it had a happy, the electron one had a happy ending, even though it annihilated. All right, may I see the specs there on this problem?
Yeah.
All right, thank you.
Mhm.
All right, so I've got basically a coordinate axis here, 0, 0. And this is like 9, 9 meters away, and it hits here. Set up I hat, J hat. And the electron is, the initial speed of the electron, initial velocity of the electron is 20,000 meters a second, I hat. And so 9 meters that way, this is 0.9 meters, 7 meters, and this is 14 meters total. Acceleration of the electron and electric field strength, and I know that my electric field is equal to basically EJ hat. I'll worry about a plus or minus in just a moment. All right, so it's an electron that is being shot here. The electron is being forced in the positive J hat direction. What is the direction of the electric field?
Well, it says uniform in a positive J hat direction, but it wouldn't move that way, and well, it could just be slowing it down enough.
Oh, except it was shot straight across. Let me see the wording, perhaps that was just bad wording on my part. Just to mess with your head. The intent was
There's probably an electron going down.
yeah, no, the intent was that the electric field, treat the electric field as going in that direction, and then realize that, oh, it's actually going that way. That, the intent was, yeah, now I see that could be misleading. So my electric field ultimately is going in that direction. It's quite, I'm trying to think of whether I expected them to throw the minus sign into the magnitude bit. The electric field is uniform. The force, therefore, on the electron is uniform. The acceleration of the electron is uniform. So what do you know about the shape of this curve?
Perfect square parabola.
Yeah, it is indeed a parabola. Going through the origin. So
1/2 AT squared.
I know how fast it's going horizontally. The horizontal velocity should not change because the acceleration is perpendicular to that. So I can figure out how much time it takes to get across. VIT plus 1/2 AT squared. Acceleration is 0 horizontally, and so I have 9 is equal to 20,000 times t. And so time would be 4.5 times 10 to the negative 5th seconds. No, negative 4th. So that's the time it takes to get across. Horizontally, sorry, or vertically, as you kids say today. Delta, oh, what the heck? Let's go with the brainwashing. Delta y is equal to VIY, t plus 1/2 AT squared. My initial velocity in the y direction is 0, because it's shot horizontally. And so we end up with 7 is equal to 1/2 a times 4.5 times 10 to the negative 4th squared. So then we find the acceleration. I know that F equals ma. And sticking to it. I know acceleration. The mass of the electron is something you can look up, but presumably on the first page, 9.11 times 10 to the negative 31st. kilograms, acceleration of whatever that is. And that will tell me the force. The force is caused by an electric field, so that should be equal to Q E hat. And so negative 1.6 times 10 to the negative 19 times whatever the strength of my electric field is. Or negative E, depends on how you handle that negative sign.
Negative 31 is in grams or kilograms?
This right here,
Yes.
this is kilograms.
Thank you.
And then solve, so acceleration is part A, and then part B, solving for E.
One point six times 10 to the negative 19th is the charge of the electron.
Negative 1.6 times 10 to the, yes, this, that's the charge of the electron, with a minus sign in there. Austin, did it answer your question?
Still not sure what the acceleration is, but
Oh,
I think we probably have the, tools to figure it out.
yeah, the equation's there.
Yeah.
It's like 6.9 times.
What'd you get?
6.9 times 10 to the
6.9
times 10 to the 7.
times 10 to the 7 meters per second squared.
Okay, and so then the electric field is just following that equation over there for the force.
Yeah, so
Okay.
the charge of, or sorry, the mass of the electron times the acceleration
Mhm.
divided by the charge.
Yeah, okay. Alright.
Other questions? Precious?
This is from spring 2015, number 8. Actually,
Okay. So we have the bent, so 15. So 15 minus 20.
Can you repeat the test?
it is, spring 2015, number 8.
Thank you.
XYZ, like that?
Yes.
Alright, and my surface is bent. Let's see, horizontal and then down. Something like that.
Surface is actually on the other side. Like, the other side of the Z. Or I don't know if that makes a difference.
Oh, it actually, it does not make a difference,
Okay.
but, okay. So my drawing officially has the x-axis there. So this is 10 centimeters this way, that's 5 centimeters that way, and then 5 centimeters bending down. So I have a 10 by 10, which I basically bend in half. My electric field was 15 newtons per coulomb I hat minus 20 newtons per coulomb J hat. And I think the first was, what are the area vectors? Because you can get multiple answers depending upon how you treat this. Although you should be consistent of, even though this is an open surface, this is one object here. So my area vector is either pointing in the positive y direction and negative x direction, or the negative y direction, positive x direction. Don't have one up here and then one going like that. So stick to one surface, one side of the surface.
The goal of the question?
Pardon?
The goal of the question?
The first part was, what are the area vectors of the two halves? So my magnitude is 0.1 times 0.05 square meters. That's my magnitude. 0.005 square meters. I'm going to call this surface right here in the XZ plane as surface 1, and the other one is surface 2. So my area vector 1 is that magnitude, which is just straight up what's the area of it. And let's make this I and J directions right there. And then pointing up, so that would be J hat. My area vector for 2, well, since I've chosen this side of it, I have to stick with that side of it, and so the other area vector would be in the negative x direction, so negative 0.005 square meters I hat. So then, I think part B was what's the flux?
Yeah.
My electric field is uniform, and so my electric flux is just E dot A. Since I have two surfaces here, it's going to be the electric flux of 1 plus the electric flux of 2. And so this becomes 15. I'm going to drop the units for right now. Minus 20 J hat dot 0.005 J hat plus 15 I hat minus 20 J hat dot negative 0.005 I hat. I think similar to, there was a master set problem where instead of having the surface bent, I had a straight surface, but I had the electric field as two separate values. And so now, doing a dot product, so I multiply the like components, and so I think it's 0.1, negative 0.1, plus negative 0.075.
Yeah.
So, which gives you negative 0.175, and then let's not forget units, Newton meter squared per coulomb.
Then for the last part, if the electric field is caused by a very large, very thin metal plate with a uniform charge density, which is 5 centimeters from the z-axis. So the first part is, what is the plane in which the plate exists?
And pain in the butt. All right. So it's going this way and down. So my electric field is basically in that direction right there. And it's, my z-axis is coming out of the board here. This is my x and y. It's 5 centimeters from the z-axis.
Yes.
Okay, so I basically have two different solutions here. It's going in that direction, and, sorry, 5 centimeters away
From the z-axis.
from the z-axis. So 5 centimeters from the z-axis. So it actually has to be on this side over here. If it's on this side over here, it'll interfere with the plate here, and suddenly my electric field can't be constant. Because it will be going, if it's a positive plate, going in two directions like that. And so the tip here would have electric field going one way, whereas the other side would have it going the other way, so we basically need the field here. It's perpendicular because I know that the electric field coming from an infinitely large plate is perpendicular to the plate. And this distance here is 0.05 meters. And there's some fancy ways of doing this, but I don't have the fancy ways at the tip of my hat, or tip of my tongue, or finger, whatever is appropriate. So let's do it a little brute force. What I need to find here is, remember that if I've got a three-dimensional shape, I basically have x, y, and z components. But since the z component is irrelevant because it's basically, the value of z can be almost anything, all I need to do is come up with the equation of that line. So the slope of this is negative 20/15, or reduced down to negative 4/3. And perpendicular is the negative reciprocal, so the slope of this is 3/4. I know that distance there is 5 centimeters, and so next we have, probably need that in a moment. Let's see, I know that's 0.05. I know this is y is equal to 3/4 x plus b. That's my b right there. This is b. I just need to find that angle.